There should be 10,000 civilizations in our galaxy alone. Not might be, not could be, should be. The mathematics is inescapable. Our galaxy contains roughly 400 billion stars. Even conservative estimates suggest billions of Earth-like planets exist in habitable zones. Life arose on Earth almost immediately after conditions allowed, within a few 100 million years of the planet cooling. Intelligence evolved, technology emerged. Scale these numbers across cosmic time, and the conclusion is unavoidable. The Milky Way should be teeming with intelligent life. We should see evidence everywhere: megastructures harvesting starlight, radio signals crossing the void, probes visiting every star system. The galaxy should be colonized, explored, transformed. Instead, we see nothing, hear nothing, detect nothing. In 1950, physicist Enrico Fermi was discussing the possibility of alien life with colleagues when he suddenly stopped and asked, "Where is everybody?" That simple question has haunted science for 7 decades. It's become known as the Fermi paradox, and it represents one of the most disturbing mysteries in all of science. Because the silence we observe shouldn't exist, the emptiness we see violates probability so completely that something must be profoundly wrong with our assumptions about life, intelligence, or the universe itself. Today, we journey through evidence that challenges everything we thought we knew about our place in the cosmos. Summer 1950. Los Alamos National Laboratory, New Mexico. Enrico Fermi, the physicist who created the first nuclear reactor and helped develop the atomic bomb, was having lunch with colleagues Emil Konopinski, Edward Teller, and Herbert York. They were discussing a recent spate of UFO sightings and a New Yorker cartoon about aliens stealing garbage cans. The conversation wandered from UFOs to faster-than-light travel to the probability of life elsewhere, standard lunchtime speculation among physicists. Then Fermi went quiet. His colleagues saw the look they'd come to recognize. He was calculating something in his head. Fermi was famous for his ability to make rapid, accurate estimates using basic principles and rough numbers. They called them Fermi problems. Suddenly he spoke. Where is everybody? The question seemed to come from nowhere, but Fermi had just performed a mental calculation that revealed something deeply troubling. He'd estimated how long it would take an advanced civilization to colonize the entire galaxy, even traveling at a small fraction of light speed. His answer? 10 million years, maybe less. The galaxy is 13.6 billion years old. Earth is 4.5 billion years old. The first Earth-like planets formed when the universe was just 1 billion years old, planets that had an 8 billion year head start on us. If even one civilization had arisen in the galaxy before us and developed interstellar travel, they should have colonized everything by now. They've had hundreds of millions of years when the job would take only millions. Where are they? In 1961, astronomer Frank Drake formalized Fermi's question mathematically. Drake was organizing the first conference on the search for extraterrestrial intelligence, SETI. He needed a framework to structure the discussion, so he created an equation, not to calculate a precise answer, but to identify what we need to know. The Drake equation multiplies 7 factors. N equals R times Fp times Ne times Fl times Fi times Fc times L asterisk. N equals the number of civilizations in our galaxy capable of communication. R asterisk equals the rate of star formation in our galaxy. Fp equals the fraction of stars with planets. Ne equals the average number of planets that could support life per star with planets. Fl equals the fraction of those planets where life actually develops. Fi equals the fraction of life-bearing planets where intelligence evolves. FC equals the fraction of intelligent species that develop technology detectable across space. L equals the length of time such civilizations emit detectable signals. When Drake first wrote this equation in 1961, most of these values were pure guesses. But over the past 6 decades, we've actually measured several of them. Here's what we now know. R* equals approximately 1.5 to 3 new stars per year in our galaxy. We know this from observations of star-forming regions. FP equals close to 1. The Kepler Space Telescope discovered that nearly every star has planets. This isn't speculation anymore, it's confirmed observation. NE equals at least 0.2, possibly much higher. Kepler found that roughly 20 to 50% of Sun-like stars have Earth-sized planets in the habitable zone, the region where liquid water can exist. These first 3 terms alone tell us something remarkable. There are billions of potentially habitable planets in the Milky Way. Conservative estimates suggest 40 billion Earth-like planets in our galaxy. Other calculations push that number to 300 billion or higher. But it's the remaining terms that create the paradox. For the next 3 terms, FL, FI, FC, we have exactly one data point: Earth. On Earth, life arose almost immediately. The planet formed 4.5 billion years ago. It was being bombarded by asteroids and was completely inhospitable for hundreds of millions of years, yet we have evidence of life in rocks 3.8 billion years old, possibly even 4.1 billion years old. Life didn't wait. As soon as conditions permitted, life emerged. This suggests FL, the fraction of habitable planets that develop life, might be high. If life arose on Earth in the first few 100 million years, maybe abiogenesis isn't that rare. Maybe, given the right chemistry, life is almost inevitable. Intelligence took longer. Simple life existed for billions of years before multicellular organisms appeared. But once they did, evolution produced intelligence relatively quickly. Tool use, language, technology, these emerged in just a few million years of primate evolution. And once intelligence arose, technology followed almost immediately. From the first stone tools to radio telescopes took just 2.5 million years, a cosmic eye blink. This is the Copernican assumption. Earth is typical. We're not special. What happened here should happen elsewhere. If that's true, then plug reasonable numbers into the Drake equation and you get thousands to millions of technological civilizations in our galaxy right now. Even if you use conservative estimates, assuming intelligence is rare, assuming technology is rare, assuming civilizations are short-lived, you still get dozens to hundreds of civilizations. But here's the problem. We've been looking for 60 years. We've searched thousands of star systems. We've listened across vast swaths of the electromagnetic spectrum. We've analyzed megastructures, looked for industrial pollution in exoplanet atmospheres, searched for signs of asteroid mining or stellar engineering. Nothing. The silence is absolute. But the evidence forces us to confront an uncomfortable possibility. Something is wrong with the Copernican assumption. Either we're not typical, or intelligence isn't typical, or something stops civilizations from becoming detectable. Something we haven't accounted for. In 1960, astronomer Frank Drake pointed a radio telescope at 2 nearby Sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial signals. He heard nothing. But Project Ozma, as it was called, marked the beginning of the search for extraterrestrial intelligence. Since then, SETI has expanded dramatically. The Allen Telescope Array in California, the Arecibo Observatory before its collapse, the Green Bank Telescope, and now the Breakthrough Listen initiative have searched millions of radio channels across thousands of star systems. Breakthrough Listen, funded by Yuri Milner, is the most comprehensive search ever attempted. It's surveying 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies. The project analyzes billions of radio channels simultaneously, looking for patterns that couldn't be natural. They've found anomalies, brief, strange signals, but nothing repeatable, nothing confirmable. The most famous signal remains the WOW signal, a strong narrowband radio signal detected in 1977 that lasted 72 seconds and never appeared again. It came from the direction of Sagittarius. It had all the characteristics of an artificial transmission, but it never repeated and we never found its source. Recent analysis suggests it might have been a passing comet releasing hydrogen, or it might have been interference, or it might have been exactly what it looked like. A brief transmission from another civilization that we'll never hear again. We don't know. But here's what we do know. Despite 6 decades of searching, despite checking millions of channels around thousands of stars, we have found 0 confirmed signals of extraterrestrial intelligence. The silence is deafening. In the 1960s, physicist Freeman Dyson proposed that advanced civilizations would eventually need more energy than their planet could provide. The logical solution? Build structures to capture more of their star's output. A Dyson sphere, or more practically, a Dyson swarm of satellites, would capture a significant fraction of a star's energy. From our perspective, such structures would create distinctive signatures. The star would appear dimmer in visible light, but brighter in infrared, as the structure re-radiates absorbed energy as waste heat. Astronomer Jason Wright at Penn State led a search for these signatures. The Glimpsing Heat from Alien Technologies, or GHAT survey, examined 100,000 galaxies using data from NASA's WISE infrared telescope. The idea, if even a small fraction of stars in a galaxy had Dyson spheres, the entire galaxy would show an unusual infrared excess. They found a few dozen galaxies with high infrared emissions, but in every case, the signature could be explained by dust and star formation, natural processes. Not one galaxy showed the distinctive pattern expected from widespread stellar engineering. Then came Tabby's star. In 2015, astronomer Tabitha Boyajian discovered that KIC 8462852 was dimming in bizarre, irregular patterns. It would fade by up to 22%, far more than any planet could explain, then return to normal brightness. The dimming patterns were chaotic, asymmetric, completely unlike anything seen before. Could it be a partially constructed megastructure? Scientists worldwide investigated. They studied the star in every wavelength, analyzed decades of photographic plates, ran countless models, and they found a more mundane explanation. Dust, probably from a disintegrating comet or planetesimal. Not aliens. Never aliens. The pattern repeats. We find anomalies, we investigate, we find natural explanations. Scientists discovered that not all regions of the galaxy are equally hospitable to life. The galactic center is a radiation nightmare. Supernovae explode frequently. Stellar density is so high that gravitational interactions would regularly disrupt planetary orbits. The supermassive black hole Sagittarius A star periodically flares, bathing the region in deadly radiation. Life near the galactic core would be sterilized repeatedly. The outer edges of the galaxy have a different problem: metallicity. Stars there formed from pristine hydrogen and helium, without the heavy elements needed for rocky planets and complex chemistry. No iron, no silica, no carbon. No planets like Earth. This defines a galactic habitable zone, a ring roughly 13,000 to 33,000 light-years from the galactic center where conditions favor life. Our solar system sits at about 26,000 light-years from the center, right in the middle of the habitable zone. Here's the problem. Even restricting ourselves to the galactic habitable zone, there should still be hundreds of millions of potentially habitable planets, and our galaxy has had those conditions for billions of years. One study calculated that if a single civilization began expanding outward at just 10% the speed of light, a technologically plausible speed, it could colonize every star system in the galactic habitable zone in less than 50 million years. The galaxy is 13.6 billion years old. Life could have started elsewhere billions of years before Earth even formed. They've had time to colonize the galaxy hundreds of times over. But this represents just one piece of a much larger puzzle hidden in the nature of intelligence itself. The most remarkable discovery involves a concept introduced by economist Robin Hanson in 1996. Hanson proposed that something prevents primitive life from becoming spacefaring civilizations. He called it the Great Filter, a stage in evolution or development that almost no species passes through. The filter could be behind us or ahead of us. If it's behind us, then the step from non-life to life is extraordinarily rare, or the step from simple to complex life, or from complex life to intelligence. We passed through something incredibly improbable, and most planets never do. This would explain the silence. We're alone not because civilizations destroy themselves, but because they never arise in the first place. But if the filter is ahead of us, the implications are terrifying. It would mean that something we haven't encountered yet, destroys civilizations before they become visible across interstellar distances. Nuclear war, artificial intelligence, nanotechnology, climate collapse, something. And we're approaching it. Evidence for each possibility exists. The behind us scenario is supported by the extreme rarity of several key transitions in Earth's history. Life took 500 million years to emerge, but once it did, it persisted. Simple, single-celled life dominated Earth for 3 billion years before complex cells evolved. That transition, prokaryotes to eukaryotes, happened exactly once in Earth's history, despite billions of years of opportunity. The evolution of multicellular life, sexual reproduction, intelligence, each of these might be filter candidates. But the ahead of us scenario is supported by something more disturbing, the Fermi paradox itself. If civilizations commonly survive and expand, we should see them. The fact that we don't suggests something stops them. Recent research has identified potential filter mechanisms ahead of us. Carl Sagan worried about this deeply. He argued that technological civilizations might have a brief window, perhaps just a century or two, between developing radio astronomy and destroying themselves. The logic is compelling. Technology capable of broadcasting across space is technology capable of self-annihilation. Nuclear weapons, biological warfare, environmental collapse, runaway artificial intelligence. These all emerged at roughly the same stage of development as radio telescopes. If the average technological civilization lasts just a few hundred years before destroying itself, that would explain the silence. At any given moment, there might be only a handful of active civilizations in the galaxy, separated by thousands of light years. We'd never detect each other's brief transmissions. The statistics are grim. Humanity has possessed nuclear weapons for 80 years, just 0.0000018% of Earth's existence. We've had radio for 130 years. In cosmic terms, we've been detectable for an instant. We also nearly destroyed ourselves several times already. The Cuban Missile Crisis, Stanislav Petrov's decision not to launch during a false alarm in 1983, multiple near misses during the Cold War. And nuclear weapons are just one threat. Climate change, engineered pandemics, artificial superintelligence, we're creating more existential risks as we advance. Some researchers argue this explains the Fermi paradox perfectly. Civilizations arise, develop technology, and destroy themselves within a few centuries. The galaxy is full of ruins, not broadcasts. But there's a problem with this explanation. It requires every civilization to fail. Not 99%, not 99.9%, every single one.
because if even a tiny fraction survives, just 1 in 1,000, they would spread across the galaxy and become visible, unless something prevents expansion entirely. In 1973, radio astronomer John Ball proposed something unsettling. What if they're here, watching us, and deliberately staying hidden? The zoo hypothesis suggests that Earth is being observed by advanced civilizations who have chosen not to make contact. We're a nature preserve, a protected site, studied but not interfered with. This idea was later reinforced by Star Trek's Prime Directive, a fictional protocol prohibiting contact with pre-warp civilizations. But the concept might reflect a real principle that advanced civilizations follow. The reasoning? If you're an advanced civilization expanding through the galaxy, you encounter younger civilizations constantly. Making contact could contaminate their development, destroy their culture, or simply change what makes them interesting to study. So, you watch from a distance. Recent research by astronomers like Douglas Vakoch at METI International has explored whether this could explain the silence. The mathematics suggests that if advanced civilizations coordinate, if they share information about young civilizations and agree not to interfere, Earth could be in a designated observation zone. But this raises disturbing questions. How many observers are watching us? Are they measuring our development, waiting for some threshold? And what happens when we reach it? Some researchers go further. They propose that the galaxy is already colonized, just not in ways we recognize. Advanced civilizations might exist in forms we can't detect, uploaded consciousnesses, nanoscale intelligences, beings operating in dimensions we can't perceive. We might be looking for smoke signals while they're using quantum entanglement. The evidence extends beyond simple absence into the realm of possibility space itself. All the ways we might be wrong about what intelligence looks like, how it communicates, or whether it even wants to be found.
This forces us to reconsider fundamental assumptions about the nature of interstellar civilizations. Chinese science fiction author Liu Cixin popularized a chilling solution to the Fermi paradox in his novel The Dark Forest. While it's fiction, the underlying logic has been seriously analyzed by scientists. The dark forest hypothesis suggests that the universe is full of civilizations, but they all remain silent because communication is suicidal. Here's the reasoning. Space is vast, and communication is slow. By the time you detect another civilization and send a message, they could have developed technologies far beyond yours. They might be friendly, they might be hostile. You can't know. If the cost of being wrong is extinction, the safest strategy is to remain hidden and destroy any civilization you detect before they can threaten you. The galaxy becomes a dark forest where every civilization is an armed hunter, moving silently between the trees, knowing that the first to make a sound dies. This explains the silence perfectly. Everyone is hiding. We're hearing nothing because broadcasting your location is suicide. Astrophysicist David Brin has explored this concept seriously, calling it dangerous METI, the danger of messaging extraterrestrial intelligence. He argues that humanity's attempts to broadcast messages to the stars might be catastrophically reckless. We've already done it. In 1974, we sent the Arecibo message toward the globular cluster M13. In 2008, we broadcast 501 messages toward Gliese 581. Private organizations are planning more. If the dark forest hypothesis is correct, we might be painting a target on ourselves.
In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published Rare Earth, proposing a comprehensive solution to the Fermi paradox. Their argument, Earth-like planets are common, but Earth-like conditions for complex life are extraordinarily rare. The list of coincidences required for complex life is staggering. Jupiter, our gas giant, shields Earth from asteroid impacts. Without Jupiter's gravitational influence, Earth would be hit by extinction-level impacts far more frequently. Complex life would never have time to evolve. The Moon, our unusually large moon, stabilizes Earth's axial tilt, preventing wild climate swings that would make complex life impossible. The Moon formed from a collision with a Mars-sized object, a rare, possibly unique event. Plate tectonics. Earth's active geology recycles carbon, regulates climate, and creates diverse environments. Most rocky planets are geologically dead, like Mars. The galactic orbit. Earth orbits the Sun, and the Sun orbits the galactic center in a nearly circular path. This keeps us in the galactic habitable zone and minimizes our exposure to supernovae and other hazards. Timing. Earth formed when the galaxy had enough heavy elements for rocky planets, but before stellar density made gravitational disruptions common. Magnetic field. Earth's molten iron core generates a magnetic field that shields us from solar wind and cosmic radiation. Mars lost its magnetic field and became a dead world. Each of these factors might be individually uncommon. Together, they might be nearly unique. Ward and Brownlee argue that microbial life might be common, but complex life requires so many coinciding factors that Earth might be one of a handful of such planets in the entire galaxy. If true, the Fermi paradox evaporates. We're alone because the conditions for intelligence are almost impossibly rare. But recent exoplanet research has challenged this view. We've found planets in the habitable zone of other stars. Some orbit in stable systems, some show signs of moons. The more we look, the more potentially Earth-like worlds we find. The rare Earth hypothesis might explain why we haven't seen aliens yet, but it struggles to explain why we haven't seen them anywhere in the observable universe across billions of galaxies.
Recent breakthroughs suggest we're on the verge of answering the Fermi paradox definitively. The James Webb Space Telescope, launched in 2021, can analyze exoplanet atmospheres with unprecedented precision. It's searching for biosignatures, oxygen, methane, phosphine, combinations of gases that only exist together when produced by life. If we detect biosignatures on a nearby exoplanet, it would prove that life arises independently. It would tell us that FL in the Drake equation is not negligibly small. And if life is common, the Fermi paradox becomes even more paradoxical. The square-kilometer array, currently under construction, will be 50 times more sensitive than any existing radio telescope. It could detect airport radar from planets hundreds of light years away. If there are civilizations broadcasting, SKA will find them. Breakthrough Starshot, an initiative to send tiny probes to nearby star systems at 20% light speed, could reach Proxima Centauri in just 20 years. If successful, we'd have close-up images of the nearest exoplanet by mid-century. We're also getting better at detecting technosignatures, artificial signatures in stellar spectra, unusual light curves, atmospheric pollution, heat signatures from Dyson spheres. Penn State's Technosignatures Group is cataloging every possible way an advanced civilization might alter its environment in detectable ways. Industrial pollutants, artificial lighting, stellar engineering. They're creating search protocols for each. Within the next few decades, we'll survey millions of stars for both biosignatures and technosignatures. We'll analyze thousands of exoplanet atmospheres. We'll have the capability to detect civilizations as advanced as our own across hundreds of light years. If they exist, we'll find them. If we find nothing, that tells us something profound about the universe.
What happens if we detect a signal? The SETI post-detection protocol is surprisingly simple. Verify the signal, confirm with independent observations, inform the scientific community, the UN, and governments. do not respond without international consensus. But the reality would be far more chaotic. A confirmed detection would be the most significant discovery in human history. It would instantly answer the Fermi paradox. They exist. We're not alone. The great filter, if it exists, is behind us. Or is it? A signal tells us only that a civilization existed when the signal was sent. If it comes from 1,000 light years away, we're seeing them as they were 1,000 years ago. They might be extinct now. We might be hearing a ghost. And what would the message contain? A greeting? A warning? A philosophical treatise? Instructions for building something? Should we respond? This question divides the scientific community. Some argue that any civilization capable of interstellar communication is necessarily peaceful. They survived their own technological adolescence. Others warn that we have no basis for assuming alien motivations align with human values. Stephen Hawking warned against contact. He pointed to human history. Whenever a more advanced civilization encountered a less advanced one, the results were catastrophic for the less advanced civilization. But remaining silent might be pointless. We've already advertised our presence. Over a century of radio and television broadcasts have created an expanding sphere of electromagnetic radiation. Anyone within 100 light years with sensitive enough receivers could detect us. We're already visible. The question is whether we continue broadcasting intentionally.
The most radical explanations for the Fermi paradox involve questioning the nature of intelligence itself. Futurist Ray Kurzweil and others propose that biological intelligence is a brief transitional phase. Once a civilization develops advanced computing, it uploads consciousness into digital substrates. Post-biological intelligence doesn't need planets, stars, or physical resources in the same way. Such civilizations might be computationally efficient, operating at small scales. They might exist inside Dyson spheres we can't distinguish from natural objects. They might even have retreated into virtual realities, creating simulated universes more interesting than the physical one. If most advanced civilizations go digital, they become invisible. They're not sending radio signals because they're not using radio. They're not building megastructures because they don't need them. They might exist on a single planet running simulations vastly more complex than our entire observable universe. This connects to the simulation hypothesis. Perhaps we're already inside one of those simulations. Perhaps the universe we observe is a simulation run by a post-biological civilization. The Fermi paradox is solved. We're alone in the simulation because the creators designed it that way. This is unfalsifiable speculation, but it's scientifically coherent, and it would explain why we see no evidence of advanced civilizations. We're looking in the wrong place, at the wrong scale, for the wrong kind of intelligence. The universe might be teeming with consciousness, just not in forms we recognize.
The most profound implications emerge when we consider what the Fermi paradox means for humanity's future. If we are alone, if the great filter is behind us, if Earth is truly rare, if intelligence almost never evolves, then we carry an enormous responsibility. We might be the only consciousness in the galaxy, possibly the only consciousness in the observable universe, the only matter capable of understanding itself. Carl Sagan called this the cosmic perspective. He argued that if we're alone, then preserving our civilization becomes a cosmic imperative. We're not just protecting humanity, we're protecting the universe's capacity to know itself. Destroying ourselves through nuclear war, climate catastrophe, or AI misalignment wouldn't just be a human tragedy, it would be a cosmic one. The light of consciousness would go out, possibly forever. But there's another possibility. If the great filter is ahead of us, if civilizations commonly destroy themselves before becoming interstellar, then our survival becomes even more urgent. We might be approaching the same trap that destroyed countless civilizations before us. The question becomes, can we be the first to pass through?
Some researchers believe the answer is yes, but only if we explicitly recognize the danger. Organizations like the Future of Humanity Institute at Oxford and the Center for the Study of Existential Risk at Cambridge are studying global catastrophic risks precisely because the Fermi paradox suggests they might be universal. We have advantages previous civilizations might not have had. We know about the paradox. We can look for the filter. We can develop strategies to survive threats we've identified. But we're in a race between our wisdom and our technology.
Here's what makes the Fermi paradox so frustrating. Dozens of solutions exist, and many are scientifically credible. Life is common, but intelligence is rare. The billion-year dominance of single-celled life on Earth suggests that the step to complex life is difficult. Intelligence might be even rarer. Intelligence is common, but technology is rare. Dolphins are intelligent, octopuses are intelligent, but neither developed technology. Intelligence doesn't automatically lead to tool use, language, or science. Technology is common, but civilizations are short-lived. Self-destruction filters out most technological civilizations within centuries of their emergence. Civilizations exist, but don't communicate. The costs of broadcasting might outweigh the benefits, or they've moved beyond electromagnetic communication to something we can't detect. We're first. Someone has to be. Perhaps the universe is still young for intelligence. Perhaps we're among the first civilizations to arise. They're here, but hiding. The zoo hypothesis. We're being observed, but not contacted. We're living in a simulation. The universe we observe is artificial, designed without other civilizations. Space is too vast. Even if thousands of civilizations exist, they might be separated by such distances that contact is impossible. Each solution has evidence supporting it. Each has problems, and critically, more than one could be true simultaneously. The universe might be full of microbial life, but devoid of complex organisms. Intelligence might be moderately common, but technological civilizations might be short-lived. The combination of filters, each individually passable but collectively insurmountable, might explain the silence. We don't know which explanation is correct. We might never know.
But uncertainty itself carries implications. We cannot assume we're alone. If we destroy ourselves, we might be extinguishing the only technological civilization in the galaxy, or we might be just another statistic in a long list of failed species. We cannot assume we're safe. If the great filter is ahead of us, complacency could be fatal. We cannot assume contact is safe. If we detect a signal, responding might be humanity's last mistake. But we also cannot stop searching. The question, are we alone, is too fundamental to leave unanswered. It speaks to our deepest sense of place in the universe. SETI will continue. Exoplanet characterization will improve. Techno-signature searches will expand. Within decades, we'll have surveyed enough stars and analyzed enough atmospheres to significantly constrain the solutions to the Fermi paradox. 3 outcomes are possible. We find evidence of life. This would be the most momentous discovery in history. It would tell us that life is common, that we're part of a larger cosmic community, even if we're separated by unbridgeable distances. We find evidence of intelligence. This would answer the Fermi paradox definitively. It would raise new questions about contact, communication, and cooperation across stellar distances. We find nothing. This might be the most profound outcome. It would suggest we're either alone or the filter mechanisms are so effective that civilizations almost never become detectable. It would place an enormous responsibility on humanity. We might be consciousness's only representative in the cosmos. Each outcome transforms our understanding of our place in the universe.
We began with Enrico Fermi's simple question: where is everybody? 7 decades later, we have dozens of possible answers and no definitive solution. The Fermi paradox remains one of the deepest mysteries in science. What have we learned? We've learned that the universe should be full of life. The number of potentially habitable planets is staggering. The chemistry of life seems straightforward. The time available is enormous. We've learned that despite this, we see no evidence of other civilizations. No radio signals, no megastructures, no sign that the galaxy has been colonized, explored, or even visited. We've learned that this silence demands explanation. Something is wrong with our assumptions about life, intelligence, or cosmic expansion. We've learned that the answer, whatever it is, will tell us something profound about reality. If we're alone, we're miracles. If we're not alone but civilizations destroy themselves, we're in danger. If we're not alone and they're hiding, we might be in even greater danger. But vast unknowns remain. We don't know how common life is. We don't know how common intelligence is. We don't know if technological civilizations typically survive or self-destruct. We don't know if the galaxy has been colonized by post-biological intelligence we can't detect. What we do know is this: the answer matters. If we're alone, then every extinction, every species loss, every human death diminishes the universe's capacity to understand itself. We become cosmically precious. If we're not alone, then discovering our neighbors becomes humanity's greatest quest. Understanding them, communicating with them, perhaps one day meeting them, this would transform our civilization beyond recognition. The search continues. Radio telescopes scan the sky. Space telescopes analyze distant atmospheres. Researchers develop new ways to detect intelligence across cosmic distances. And somewhere, perhaps in our lifetimes, perhaps in our children's, we'll find an answer to Fermi's question: where is everybody? We're looking, we're listening, and one way or another, we're going to find out. The universe is vast, the mysteries are endless, and we have only just begun to ask the right questions.